Okay. In mathematics, we like proof that something is true. We are going to talk about mathematical induction, which is a proof strategy that we can use based on a sequence. Have we been, well, I know it's been what feels like a while because there's Thanksgiving thrown in there, but we have been working on sequences. Yes? At some point in this chapter. Okay, we've gone kind of out of order. Okay? Before I begin with what this proof strategy is, number one, it is not like your two-column proofs in geometry. Okay? You will not have to give a reason for everything like you did in geometry. But there is a specific process that you need to take, and it's mostly algebra that we're going to be doing within our proof. Okay? Like distributing and factoring and things like that. Okay? But first we got to kind of get used to the notation. So first of all, let me tell you what the steps for this proof are. Talk about why they work, and then we're going to work on some notation first. Okay? So first of all, you're going to get a statement, and it's going to look like an equation. It's basically going to look like a formula. Okay? You're going to get a formula, and it's going to be in terms of n, which we assume to be integers. The principle states that if, number one, the first term is true, what this means is you plug in 1 to your formula and it works. So if 1 is true, and we're going to change it up. We're not going to use n. We're going to change to k's inside of our proof. So number 2, if for any k, pk implies the truth of p sub k plus 1, if those two things happen, then our statement is true for all numbers. Write it down. Don't try to process it quite yet. Just write it down. Okay, so these are the steps. This is what mathematical induction says. We have a statement. We show, but plugging 1 in for n makes it a good statement. Then we show that p sub k implies p sub k plus 1 is true. And if those two things happen, then we can conclude that our statement is true for all integers n. Okay? Why is that the case? Okay, I want you to think of dominoes. Okay? If you set up dominoes, here, I think I have the slide. Okay? You set up dominoes and you want them all to get knocked over, right? Okay? Mathematical induction is kind of like setting up dominoes. If I can prove to you that any given domino, like K, if I can show you that any random domino, when pushed, will knock over the next one, and as long as I show you that number 1 is true, then when I push number 1, it'll knock over number 2. And then number 2 will knock over number 3. And number 3 will knock over number 4. And so on, and so on, and so on, and so on. So if we can show that the first one is true, and as long as something is true makes the next one true, then 1 follows to 2, 2 follows to 3, 3 follows to 4, so on and so on and so on and so on. Okay? So putting those two steps together logically show us that this formula is true. Okay? The first step is going to be the easy step, showing that P of 1 is true, and we'll look at that later in the class period. Step number 2, showing K implies K plus 1. There's going to be a little bit of work with that. It's going to be a lot of algebra. But what I want to practice before we even get into that is some of the notation stuff. Okay? A lot of what we need to practice is if we have a formula, we have p sub k, what does p sub k plus 1 look like? Because we need to have an idea of where we need to go with our proof. Okay? So what I want you to do is write down p sub k. Okay. This would be only a part of our formula. I'm kind of looking at it at just one side of the equal sign. Okay, but I want to start small. What's going to happen when we get to our proof writing at the end of the period is we're going to need to figure out what p sub k plus 1 is going to look like. What do you think we're going to need to do? If this is p sub k, this is p sub k plus 1, it's kind of like function notation, okay, but we're working with sequences, so it's not function notation. K becomes?
K plus 1.
Yep. K becomes? K plus 1. So what would k plus 3 become? K plus 1 plus 3. That's what I need you to do. Riley, what'd you say?
I just don't get it. Like, I get what you did, but, like, why?
The y is going to come for too soon. Okay. Okay. We kind of need to practice the notation before we actually do the proof. So this really doesn't make sense until we actually write a proof.
What do you do? What do you do with that?
Well, once we get to our proof, like, we will want our algebra to go from equaling this to equaling this. And there's some other stuff that we're going to need to do that I'll show you. But we're kind of just practicing. If this is p sub k, this would be p sub k plus 1. Okay? On the other side of the equal sign, you could get something that looks like this. Write this down. And stop panicking. Oh. Okay, so this looks more like a sequence, right? Really the sum of a sequence, okay? You're going to see this on one side of the equal sign and then something like what we saw on the first slide on the other side of the equal sign, okay? Nothing's going to change. If our subscript is k plus 1, that just means wherever there's a k, we're going to put k plus 1. So is there a k in 2 plus 5 plus 8? No. But here, where there's a k minus 1, what would that become? Okay. And here, where there's a k, it becomes k plus 1. But since it's attached to the 3, we're going to need to be a little bit careful. Since the k is multiplied to the 3, the k plus 1 would also get multiplied to the 3. So really, it would be 3k plus 2. Do you see that? The k plus 1 has to get multiplied to the 3 before subtracting the 1. So you have 3k plus 3 minus 1. No, so this is what we're going to talk about here in about 10 minutes. Do you see how we have 2 plus 5 plus 8 all the way until 3k minus 1? Do you see here how we have 2 plus 5 plus 8 all the way until 3k minus 1? Okay, there's going to be kind of a pattern that we're going to have that we're going to be able to do some substitutions with once we have all the pieces put together. Okay, so this is what we're going to do. We're going to take a timeout. At least one person at your table is going to have a book open. And there are 4 problems on your gold sheet that you're going to practice. To be very honest, you probably only need about 5 minutes to do it, but I'll give you up to 10. Yes? It is not a coincidence because we have an arithmetic.
So that carries on even to inside the
Okay, so help me out, gold sheet people. It is on page 642. Page 642. And what numbers?
5, 6, 7, 8.
5, 6, 7, 8. Good. 9 and 10? What?
Yeah, 9. There's 6, 5 through 12.
So there's 6 problems. I'm still not changing my, it's probably only going to take you 5 minutes stance though. I'll turn the light back on. If you're watching from home, you should be doing the same thing. Yeah, recording. We're live. Just the same. feel like we have something. Right now, we're just working on. Yeah, that's what we're on.
I have myself pretty, I don't know if I get them off to this class though, or if it's my first time. So I rely on these.
Five Here's someone from.
Thank you. I'm gonna.
Sorry, I realize that you can see it. No, you're good.
K plus 1 into K. P of K. You can plug that in. That's what you're saying? That's very true. That's exactly what you did on that one. Yeah, I get where you get that from, but why do you have a plus anyway? It's both of them. But okay, so we both keep it. Just to simplify it.
Unless you want to start one to one. Because I'm going to show you and the first group in our homework is probably the simplest of the five. So if you, I think it's five. And then we go to, I think it's five.
It's five.
It's five, okay. So there's five proofs that are our homework tomorrow. My plan is to go through one proof here, go through a second proof tomorrow, and class. So that's some time to work where I can check.
copies of our we'll look at the sheet. No, and Friday the test and back to me.
So tomorrow we'll call it work study, so we'll work in class.
And then the Friday, what is the test first?
But at 8 o'clock, now let's start.
Yeah, I got that. It's so weird. I mean, like sign up to take that. So like, there's always three finals, schedules, and all. So like, you have to go my mom's one.
No, can we leave this place? Can we leave the square? Yes. Okay. Yes, that's exactly what I want. So you did keep us in square times you guys distribute that out? Oh, she didn't.
Not just at school, but like people's semester, like this is not the best thing.
Riley.
I'm just talking about how bad this semester has been. This has been a rough one.
I'm really wrong.
I love it. That's why I think that's the only reason I'm actually not. Yeah, my mom just wants me to go. So I can start. I was so bad for that. So yeah.
Okay, here are your answers.
SSS. Oh my gosh. I thought we were going to delete that whole geometry board. I thought we were going to side by side.
So the biggest one I'd be concerned about checking is number 8.
That geometry board has me messed up.
Sorry.
I always looked at the geometry.
Just make sure that k plus 1 gets multiplied to the 2 before you add the 1 to get that 2k plus 3. Okay? Any issues we need to work out of plugging in k plus 1? Are you ready for the actual thing?
I'm so confused about this. You did our homework.
Yeah, every day, yeah. Oh, because I don't know. So, like,
Okay, so does everyone still have a book out?
Yes.
Okay, look at number 11. Number 11 is the first problem I'm going to ask you to do for tonight's homework. Okay, so do you see that what we just practiced is pretty much what's on the right side of the equal sign in number 11? I mean, not exactly, but that's kind of like the concept. What's going to happen is we are going to have the sum of a sequence equals an expression. And what we want to prove is that this sum of a sequence equals that expression. Okay? How are we going to do that? We're going to do that with mathematical induction. And this is a very, very unique proof strategy that we really can only use when we have the sum of a sequence equaling an expression. Okay? Like we talked about earlier, if we show that that first domino is going to fall, and if we can prove that any random domino will knock over the next one, then 1 will knock over 2, 2 will knock over 3, 3 will knock over 4, etc., etc., etc. So math terms, if we can show that our formula works for plugging in 1, and we can show that the k formula forces k plus 1 to be true, then it will be true for all of our n integers. Okay. So I want to see two steps. Number 1, you are going to show that p sub 1 is true. This is the easiest part of your proof. You literally show me that you plug in 1 and that it works. Can you handle it? Okay. Okay, now, if you look at numbers 11 and 12 and 13, they're all written in terms of n. Do you agree? Okay, so what we are going to do is we are going to have to change it to k. So you are literally going to write assume, and then you're going to change all of the n's to k's. And then we're going to have to look at our k plus 1 sum. So if you think about it, our k plus 1 sum is going to be the same as the sum of the first k terms plus one more term. If I already know what the sum of the k terms are, then when we talk about the sum of k plus 1 terms, we're just adding one more term. Like if I asked you for the 5th partial sum, you would add up the first 5 numbers. Do you agree? If I asked you for the 6th partial sum, you would add up the first 6 numbers. Well, if you already have the 5th partial sum, wouldn't you just add in the 6th term? Mm-hmm. Like if I'm adding this sequence right here, we would call this the 5th partial sum because we're adding up the first 5 numbers, right? Okay. Well, if I asked you for the 6th partial sum, I'm just wanting the next one. So I would add in the next term. So we still have the 1, 2, 3, 4, 5, but then I added in one more term. So that's what I wanted to put numbers on it because that's what we're going to do with k's. Okay. You ready?
Yes.
We are going to go through one proof. My expectation, you can look at problem 11 in your homework tonight if you want to try to get through it. But what we will do, I think it would be a good idea for you to at least look at number 11. What we'll do tomorrow is we'll do another problem at the beginning of class, and the rest of the time will be yours to go through a problem, check it with me. Go through a problem, check it with me. Okay, because I want to make sure you're doing this right. So please write down this formula. I want to show that 1 plus 3 plus 5 plus 7 plus blah, 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 2n minus 1. Basically, the sum of the sequence 2n minus 1 is always going to be n squared. So our first step is we have to show 1. Okay? So I'll wait for everyone to get it written down. So we need to show that our formula works for n is 1. So the sum of one term, well, what is our first term? Okay. Does that equal n squared? Does 1 equal 1? Okay. Please don't just write 1 equals 1. Okay, like show me, like in this case, we had n squared. So I wrote 1 squared and then I simplified it to 1. Like I want to see you plugging that in. Okay, so that's our easy step. Step number 2. What word did I underline that I say, hey, you have to write this word? Assume. We are going to assume S sub k. Just change all of your n's to k's. Because we're talking about our random domino, essentially. We're choosing our random domino. And we got to show that it's going to knock over the next one. Okay. Well, if this is the sum of the first k terms, then the sum of our k plus 1 terms would be 1 plus 3 plus 5 plus 7 plus 2k minus 1 plus our next term. Okay? So we already had these terms added together. Now we have to add in our next term because we're talking about the k plus 1 terms. We have to add the k plus 1 term. Thank you for asking that. Addison just said, does it equal k squared? That is our goal. Okay? So we don't know what this equals, but in our proof, we need to show that it equals k plus 1 squared. How did Addison get k plus 1 squared? Max.
Because above equals k squared,
So our k sum equals k squared. A little off balance. So our k plus 1 sum, we need to show that it equals k plus 1 squared. That's the work we got to do. Okay, but let me ask you this. What do we know about 1 plus 3 plus 5 plus 7 plus blah, 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 2k plus minus 1? It equals k squared. We assumed that, right? So what can we write instead of that big thing that I underlined in red?
K squared.
Thank you. All right. But we still have this guy right here, which is the same as 2k plus what? Is that right?
Yeah.
So we have k squared plus 2k plus 1. does equal k plus 1 squared. That should happen with all of the formulas I give you to prove, because I will always give you one that's true. Okay? So what do we just do? Okay, therefore, does therefore have an E at the end?
Yes.
Okay, it looked a little bare. Okay. Therefore, what did we just show? We showed that this sum equals n squared for all integers. I do want you to give me that conclusion, okay? Let's go back to n where we started. What did we do? We showed that this formula is true for all integers n. Okay. Addison, what did you think? That wasn't that bad. Okay. Now, so technically we've already done the homework for tonight. But what you could do is you could look at number 11 because it's very similar to this one. And if you want to try to model it like this one, you have my go-ahead. But I wouldn't do more than number 11. If I were you, I would wait because I'm going to give you work time tomorrow. Okay? Turn to your neighbor and just tell them what you think about this.
It's gonna get hard. So right now.
No.